You got it.
That needed.
I left too. There's a lot.
I'm not as short as most of you.
Okay, so as you can see, my voice is a little bit better today. Hopefully back in full for Monday. I haven't taught any today. I've been giving quizzes, so this is going to strain my voice. So bear with me. And I can't obviously shout over you guys today, so make sure you guys are listening. And I'll do my best to project so you guys can hear everything. Chapter 10 ends with probably one of the easier concepts. Okay. Still has to deal with exponents. We'll still see some exponents today, but we're not talking about exponent properties. We're talking about scientific notation. And so what is scientific notation? Well, some numbers are too long, I should say. Could be really, really small, could be really, really large, but either way, they're too long to write in what we call standard form. Standard form is how you normally write numbers. So for example, if you look at the US national debt, it's really big. And it's been even updated since I posted these notes an hour ago. 26,614,497,346. Okay, it just keeps going up.
Why does it keep going up?
Okay. Now, this was last updated in April 15th of 2021. It is May. So obviously you can see that that's the projected each second. We're projecting that much more national debt. Of course, that's probably going to increase considering all the stimulus packages and stuff that have been coming out these last couple months because of the COVID virus. So we're very much in debt as a nation. So that number, if we focus on the number, that number is very long. You can say it's very, very large, and you'd be correct. It's also very long. It'd be long to write. Okay.
Is it 26 trillion?
Yes. Now, some numbers are not very big. They're very, very small and equally hard to write. So for example, the average size of an atom is about 0.00000003 centimeters across. Now, if it was 0.3 centimeters across, that'd be 3 millimeters. And that's something we can wrap our brain around. This is 0.00000003 of a centimeter. So it's not visible unless you're using a telescope. No, well, sorry, not a telescope, a microscope, right? Something, telescope's what you would see to see things that are far away. Microscope is something you would see up close and you would see much bigger. Okay. So a number that's written in scientific notation, or a number is written in scientific notation when it's represented as a product. Oops, let me get my right size here. There we go. When it's written as a product of a factor and a power of 10.
Oh, is that whenever your thing's too long on your calculator?
You guys have seen this before on your calculators. When you have a number that's too big in your calculator, and some calculators use E for exponent, right? So we're going to look at some of that today. What your calculator is doing is write it in scientific notation because it can't fit all the digits on the screen. Okay. So we write numbers that are very, very small and very, very large using exponents. What kind of exponent, or I should say using powers of 10, what kind of exponent do you think we would use for a really, really, really small number like this, Claire?
Positive?
No.
Negative?
Yes, the opposite. Yes, a negative exponent gives you a small number. We know that a negative exponent takes the number on top of a fraction, puts it on bottom, it reciprocates it, which makes it much smaller. 2 versus 1/2, 5 versus 1/5, for example. Hello? Using ACS today. I honestly don't know, but if you call the office, they should give you the extension. Right. What was I saying?
Long numbers, big numbers, negative exponents.
Yes, yes. So negative exponents obviously make your answer much smaller. We actually looked, if we go back to the exponent notes, which I don't have pulled up here, there they are. If I go back to the exponent notes, when we first talked about negative exponents, there it is. We said that when you're working in powers of 10, that you just move the decimal each time. So each decimal place is a power your ones column, 10 to the zeros, 1. You got your tens column, your hundreds column, your thousands column, and it goes the other direction as well. Tens, hundreds, thousands. If I raise a number to a power of 10, how do I say this? If I'm timesing a number by a power of 10, I should say, and that power of 10 is raised to a negative power, it's actually going to take the decimal point and slide it to the left. Versus if it's a positive exponent, it's going to slide it to the right that many times. Okay. So this is what a number that's in scientific notation will look like. You've got a factor here. You've got a power here. The factor, the power. The factor has to be a number that's between 1 and 10. It can be 1, it can't be 10. So a good way to think about the factor is that you can only have one digit in front of the decimal point. You can only have one digit in front of the decimal point. Okay? Like 8.3. I can't make that be 83. That's too big. I can't have it be 0.83. It's got to be 8.3. There has to be one number in front of the decimal point. So it can be between 1 and 10, but it has to be less than 10. It can be equal to 1, but not equal to 10. The power portion of it has to be a power of 10. If it's not a power of 10, then this doesn't work. This is supposed to be an easy way of writing numbers. It is not supposed to be a complicated way of writing numbers. If you raise it to a power other than 10, you have just complicated this way too much. Because our number system is a base 10 number system. Every time you move the decimal point, you're timesing by 10. Every time you move the decimal point this way, you're dividing by 10. So if you raise this to 9, for example, this whole thing's trashed. And you just made it way more complicated. So it's always to a power of 10, and the exponent is either positive if it's a big number, or it's negative if it's a small number. Okay.
Wait, this is the, oh, never mind, you can, never mind. That makes sense.
So
So
the
you
fact,
meant like 8 to the power of 3 was to the power of 10. I'm like, what?
no. It's being multiplied by 10 to the power of -7, actually. The factor must be greater than or equal to 1 and less than 10. Just reiterating that fact. Gotta be greater than or equal to 1, less than 10. So I kind of explained how it works, but we're going to write it down here. Each place value is a power of 10. So the exponent moves the decimal that many places. The exponent moves the decimal point. If it's a positive exponent, then it's going to move your decimal point to the right because it gets bigger. But if it's a negative exponent, it's going to move your decimal to the left because it makes it smaller. Okay, so before we do anything with scientific notation, I want to be very clear on whether or not we know what it looks like. Some of these numbers are in scientific notation, and some of them are not. I want you to identify which ones are not. And if they're not, we're going to change them so that they will be. Okay, we're going to change them so that they will be. For example, A, is this number in scientific notation?
No,
Why not?
because it's not greater than 1.
Yes, you're correct. That factor has to be between 1 and 10. That number that you're multiplying by 10 has to be between 1 and 10. And 0.9 is very close, but not between 1 and 10. So what I'm going to do to make it in scientific notation is I'm going to move the decimal point over one spot to make this just a 9 then. If I move the decimal over one spot, Devin,
We have to take away from that. So
that's
take away
exactly what I would have to do. You're right. So it should be 10 to the,
7 power.
that is correct.
So when you have to, when it's greater than 10, you have to move it to the opposite way, right?
Sure. Yeah.
And
If it's
then you
greater
have to
than-
add?
You're right.
Okay.
Yep. So what happened is because we moved the decimal to the right to make it in scientific notation, what we did is we just times by 10. So to cancel that out, since we just moved the decimal point over one spot times by 10, we just took away one of these. So we don't times by 10 too many times. Okay, we just took one away from that. both of these values, if I were to grab my calculator and take 0.9 times 10 to the 8th and 9 times 10 to the 7th, they're both equal. I'm not trying to say that this is different from this. What I am trying to say is that when they created scientific notation, they wanted a way for everyone to compare the numbers that are much bigger than the other ones and much smaller. And in order for us to compare them, we have to write them the same way. Okay, so just like there's an order of operations that says we have to do the math in these orders, in scientific notation, we have to make sure that first number is between 1 and 10. Otherwise, you can't really compare them very easily. Example B, is this in scientific notation? 5.9 is between 1 and 10?
Yes.
Okay. So I'm just going to go ahead and put S in with a check mark to show that this is already in scientific notation. We checked it. Okay. Example C, is that in scientific notation?
Yes.
Is the factor between 1 and 10? Is it being times by 10 to an exponent?
Yes.
Then this is in scientific notation. You're right, it is just 7.
I don't know why they read it scientific notation.
You
It's
would,
just examples.
there are a few numbers like this, right, which are already small. 7 is already a small number, a short number, right? So by writing it in scientific notation, you actually made the number longer. Normally, when you write a number in scientific notation, it gets shorter. Okay, but this just goes to show you that you could write any number in scientific notation, even the number 7. 7 was supposed to be written in scientific notation. You would write 7 times 10 to the power of 0 because we don't have to move the decimal at all. Example D, is this number in scientific? What's wrong with that? It's bigger than 10, right? It has to be between 1 and 10. It can be equal to 1. It can be, but it must be less than 10. The reason it has to be less than 10 is because I can take this decimal point, move it back right there. Now it's equal to 1. Right, so it can be equal to 1, but I can only have 1 digit in front of the decimal point. I can't have 2 digits in front of the decimal point. Because if it did, I could just slide it over and make the 1 digit. Okay. So for example D, by sliding the decimal point backwards 1 spot, I have to add, because by sliding the decimal point backwards 1 spot, I'm dividing by 10. So to make sure I account for that, I have to raise that exponent to 1 more power. So Max, what is one number larger than -4? -3. Good. So this is going to be 1.02 times 10 to -3rd. So when you have to increase the decimal point, you have to decrease the decimal. They're opposite of each other. When I increase the decimal point to the right, I have to decrease the exponent. If I have to decrease the decimal to the left, I have to increase the exponent, and -3 is bigger than -4. Check your integers, right? Riley, did you have a question?
Yeah, but I answered. The answer popped up.
It happens to me too. It's okay. You let me know if you get another question, okay? All right, so now that we know what it looks like, let's see if we can write numbers that are already in scientific notation in standard form. Notice all 4 of these numbers are in scientific notation. That is not the question. I'm not asking you if they're in scientific notation. I'm asking you to convert them out of it. Okay. Caleb, do you have a question?
Can I do?
Sure, go ahead.
So 0.00032.
That's correct. Nice job. So the exponent of -4 is going to take the decimal point, and because it's negative, it's going to move it to the left because that's the smaller direction. And it's going to move it to the left 1, 2, 3, 4 times. The first move just gets it around the 3. The other 3 moves, we have to put a number in there, and that number we always put in there is 0. So 1, 2, 3, and 4, those 3 gaps have to have zeros in them. So this very, very small number, 0.000322, is the same as 3.22 times 10 to the -4. They're the same number. Scientific notation is just another way of writing a number. Don't think of scientific notation as a math problem. It's just another way of writing a number. Olivia, how would I do this one?
It would be 790,000 or 799.
Okay. That's correct, 790,000. We're gonna take the decimal point because the exponent is positive. We're gonna move to the right. We're gonna move to the right 5 times. 1, 2, 3, 4, 5. The first move gets us around the 9. The other 4 moves have to be zeros. Please, when you're doing this on your work paper, don't leave your answer like this. It's kind of messy. So just write it underneath or off to the side as 790,000. Put your commas in for my own sake. When I'm grading your quizzes, it's so much easier for me to grade when I can actually see that that's 790,000. If you don't put the comma in, I have to count it and try to put the commas in myself. Okay. Do I have questions first before we go on? Just raise your hand if you have a question. Harrison.
But do we have to show that work or do we just go through?
I guess you could just write the answer, right? That's true. There's really not much work to do. I guess I'm talking about like on your quiz. When you take this on your test next week, don't take the problem on your paper and move the decimal point, put it in a bunch of zeros and write over the numbers I've already written because it's hard for me to see that. But on your work paper, you can just write the answer. That's fine. Haley, do you want to try example C? I saw that you had your hand up. 60 million. I think that's right.
Yeah.
Yep. I had to count to 7 in my head real quick. So this one doesn't have a decimal point. If it did, we'd say 6.0, right? So just put the decimal point right there after the 6. The 7 is going to move it 7 times to the right because it's a positive 7. And so I don't have any like moves to get around a number. Every single time I move it this time, it's going to be a 0 because I don't have to move it around a number. So 1, 2, 3, 4, 5, 6, 7. And I fill in with 7 zeros. And the number 60 million has 7 zeros. Okay, so that's the same number. Levi Shoemaker, do you want to try example D?
Yeah, is it 0.01285?
That is correct. The exponent is -2. It's going to move the decimal 2 spots to the left. So 0.01285. Or if you wanted to put a 0 in front of it, that's fine as well, as long as there's not 2 zeros after the decimal point. It's pretty simple stuff, right? Okay, let's look at this next question. An object with a lesser density. You guys talked about density in science class?
Yeah.
we've had that a long time.
Okay. An object with a lesser density than water will float. It's called buoyancy, right? An object with a greater density than water will sink. So if it's got a lesser density than water, it floats to the top. If it's got a greater density than water, it's going to sink. Use each given density in kilograms per cubic meter. Can't say that. To explain what happens when you place a brick and an apple in the water. I bet you could probably tell me, right? Well, let's see, just compare it anyways. Yes.
So say you have like a battleship right here. How does it float in water if it's so heavy?
It's less dense. Well, it's very heavy, right? You
Yeah.
just spread the mass out. For the same reason that if I lay on a raft, I can float, right? Because my surface area is spread out. If I stand up on the raft, it will start to sink, right? But if I just lay down on a raft, like I'm thinking like a little floaty in the pond, the pool, right? Because it spreads that out. It's less tense.
How does
Okay.
that
The raft, me and the raft actually weigh more than just me by myself, right? But if I'm on the raft, it spreads out my density more. So I'm all of a sudden I'm buoyant. Riley? Okay, we'll go back to the question. So Riley, this is the density of water. I'm not going to ask you guys to convert these out of scientific notation like we just did. I want you to compare them in scientific notation. Because one of the advantages to writing in scientific notation is they're very easy to compare.
How do you know where you're more dense because it has a bigger amount of business?
Well, that's what I was going to have Riley do.
Okay.
Riley, what were you going to say about the brick? Would the brick float or sink?
the brick is sink because it has the same, like it's both 10 to the third power, but the number being multiplied is bigger than.
That's correct. Yeah, so the first thing, when you're comparing numbers that are written in scientific notation, the first thing you want to look at is their exponent. Both of these are raised to 10 to the power of third, so they're both the same. Then you look at the factor. Water has a density of 1 times 10 to the third. Brick has a density of 1.84, so it is greater than. Because it's greater than, it's going to sink. The apple, on the other hand, although it says 6.41, what's its exponent? 10 to the second power. So it's going to be less dense, so it's going to float. So don't look at the, what I call the A value. If you hear me say the A value, I'm talking about that factor, because normally when I write in scientific notation, this is how I think about it. Okay, so don't look at the A value to determine which number is bigger. Because although 6.41 is bigger than 1.4, this is 641. This is 1,840. So the exponent makes a huge difference. Look at the exponent first, then look at the, if they have, like Riley did, if they have the same exponent, then look at the A value to see. Okay. It's like when you're comparing, it's the same thing we do when we compare decimals. Make sure you know, if I've got a 6 that's in the 10th place, and then another number has a 6 that's in the 1000th place, the 6 that's in the 10th place is more than the 6 that's in the 1000th place. So that's what the exponent tells you where that number's at. So we have to pay attention to that. A dog has 100 female fleas. How much blood do you think the fleas consume per day? The average female flea consumes about 1.4 times 10 to the negative 5th liters of blood per day. Now, I could change this problem and probably make it a lot easier and say, why are you measuring the blood in liters when you're talking about fleas? Right? They're not going to suck that much. That's why it's 10 to the negative 5th. Okay? A liter's pretty big. Right? So because they're using an object that's pretty big to measure the blood in, the flea is very small, it's going to be a very, very small portion of that liter. Okay. So that's how much they do per day, 1.4 times 10 to the negative 5th. I'm just going to write that a little bit bigger for us. Okay. A dog has 100 female fleas. So I'm going to times this by what? By 100, which is the same as timesing it by what? 10 to the second power. And so let's ignore the 1.4 for a second and just look at this portion right here. What's 10 to the negative 5th times 10 to the second?
10 to the negative third.
10 to the negative third. So this is now going to be 1.4 times 10 to the negative third liters. I don't know the abbreviation for liters, so I'm just going to spell it out. I think it's probably just an L.
Capital L.
Is it capital? Is it capital L? I knew it wasn't lowercase. Okay, that's it.
Oh,
I mean, you could times it by 100, right?
you want it in standard notation,
Well, I don't know. It didn't say. Let's write it both ways.
right?
So that's what it is in scientific notation. It was probably even easier just to leave it in scientific notation. Devin, what is it if I write it in standard form?
0.0014.
That's right. Because the negative exponent is going to move the decimal 1, 2, 3 times. And so there's extra 2 moves that have zeros there. Riley.
We also solve for 1.4 raised to the negative 5th, and then multiply that by 2.
Yeah, that's fine. You can do it that way. Because it didn't say that you had to leave this in standard form. You could have converted it to standard, didn't say you had to leave it in scientific notation. You could have converted to standard form right away. So yeah, they didn't really give us a whole lot to go with here. I feel like I was going to say something, but I forget what I was going to say.
So when you're to multiply, it always has to be 10.
Yes. When you're writing your number in scientific notation, yes. Because if we don't do it in 10, then what allows us to move the decimal so easily is that we're multiplying by 10 each time. 10 to the 5th power means times 10 times 10 times 10 times 10 times 10. I don't get to move the decimal point when I'm timesing by 9s or 8s or 4.2s. It's timesing in now the negative exponent moves us to the left. What are you actually doing when you're working with the negative exponent to the 10 to the negative power?
Are you dividing them by itself?
That's exactly what you're doing, Riley. You're dividing. When you multiply a number, an A value, for example, when I multiply this number by 10 to the negative second, I'm dividing it by 100. when I times by 10 to the negative third, I'm dividing it by 1,000. Because that's the same thing. If I told you to divide a number by 1,000, you take the decimal and you move it to 3 spots to the left. Okay? So scientific notation, because it forces you to multiply the two numbers together. Anytime that the number is small, we're going to write our division as a negative exponent. So if you're like, well, I need to divide by 1,000. Well, scientific notation says you have to multiply. Okay, fine, I'll multiply by 10 to the negative third. That's our way of getting around it. So we can divide by 10 3 times and divide by 1,000. Now, for those of you that have graphing calculators, I know some of you have worked with these before. They have the big screens, right? You have a graphing calculator, you write a number in scientific notation if it's the E on there. Some of your scientific calculators do the same thing. Okay. 8.73 E16 means 8.73 to the, yes, times 10 to the exponent of 16. That E stands for the exponent that's going to be on top of the 10, right? So that means I got to move the decimal 16 times to the left or to the right. To the right, because the 16 is positive. So that's going to be a big number. Let me write it first and you can tell me what it is. You will, because the first two moves are just going to be around the 7 and the 3, right? So 2 of my 16 moves are just going to kick me from here to there. And then I need 14 more moves. So I got to add 14 extra zeros. So I'm just going to go ahead and erase my decimal. And I'm going to add 14 zeros. Oops. Comma, 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 comma.
It's quintillion.
Yeah, 87.
Hey, it's 87, it's 87.
It's 87.
Oh, thank you. I shouldn't have spaced it out like I did.
87 quintillion.
Yeah, it's
There you go.
80, it's
87,
87 quintillion.
87, 300.
87
hundreds.
87 quadrillion.
Thousands. At the millions,
87.
Yeah,
billions,
trillions,
trillions.
quintillions.
I guess
It's quadrillion.
no, quin will be 5. Quadrillion.
Quadrillion. That's what-
Quadrillion.
87 quadrillion,
87
300 trillion.
That's a big number.
Very big. Much easier to write it like this. Much easier if your calculator could fit on a screen like that.
Graphing calculator.
Google purchased
Okay.
YouTube.
Shh. We have just finished section 7. Sorry, 7, wrong class. We've just finished section 10.5. We're now moving into 10.6. 10.6, instead of taking numbers that are in scientific notation and writing in standard form, section 10.6 is going to have us take its numbers that are in standard form and reverse them back into scientific notation. So instead of going from scientific to standard, we're going from standard back to scientific. Okay? Yes, Caleb. Sure. What is my A value going to be? Good.
No.
You got it. There you go. It's just that easy. So it says write each number in scientific notation. This is true. And probably this looks like a very expensive purchase, but this, I'm sure they've made their money back on this by now. Google purchased YouTube in 2006 for $1,650 million, sorry, $1,650 million. Now,
So I wonder if they bought it.
they bought it from YouTube.
That's
YouTube
weird
sold
because-
YouTube.
It's weird because
The $1 billion.
YouTube came out in 2005, so it couldn't have been that big in
Oh,
2006 already.
it was. It was very big.
Did you
Yep.
watch YouTube? Because you got YouTubers that Logan
Sure.
Paul. Yeah, they have one.
I didn't watch as much as I watched.
Did you know YouTube was originally like a dating app or something like that?
Yes, it
You
was.
could- you could
I think it
text
was.
people on there.
Really?
Yeah.
Yeah.
Caitlin. Yes, hang on one second. Yeah, I'll have to do the next one. So yeah, so the creator of YouTube, and this happens a lot. To a lot of companies that do that start up, the bigger corporations will buy that company out. Yeah. For example, yeah, Yahoo was actually Yahoo was very competitive with Google. Yahoo was that more people were using Yahoo than Google. For For the majority, yeah, for the majority of the 2000s to 2010s.
Like
And it
Facebook
wasn't
by-
until the 2010s that Google took over.
Yeah, like Facebook by Instagram, T-Mobile just by Sprint.
There you go.
Olivia. Like
I thought Sprint.
Olivia,
this year.
do I need to take your book? You need to take your notes now. Okay. So to take a number, put your hand down real quick. To take a number that's in standard form and to write it in scientific notation, take your decimal point and put it right after the first non-zero digit, which in this case is a 1. That's the first non-zero digit. All the other zeros can be ignored. And so just like Caleb did, we're going to write this as 1.65. Then you have to count how many times you would move the decimal back to its original location. There's its original location. I can mark it with an X. You'd have to move it 9 times. Do not count the commas as moves. The commas are not numbers. Okay, you have to move it 9 times. So you're timesing by 10, a total of 9 times. That's 10 to the 9th power. So 1.65 times 10 to the 9th. If you move to the right, it's positive. If you move to the left, that'd be because it's a really small number, and so you write it as a negative. Okay, Caitlin, you asked to do the next one.
Yeah, but, well, couldn't you like, since it has to be like below 10, can't you just like, see where, like.
Yeah, that's the same thing as putting it after that first non-zero digit. That makes it between 1 and 10. That's why I said non-zero, because if it's 0, it's not going to be between 1 and 10 anymore. So yeah, so put it where you would think it makes it between 1 and 10. And I guess what I'm saying is I've seen people on their quizzes write this number as 1.6500000000 times 10 to the 9th. That defeats the whole purpose. Why would I include all those zeros after the decimal point if I don't have to? The whole point of scientific notation is to shorten the number down. Okay. Here's another mistake I see. I'll ask students to write it in scientific notation. They'll do this, and then they'll take their calculators and take 1.65 times 10 to the 9th, and they'll get the same answer they started with.
So they just,
It's like they wrote it down and then thought, well, now what do I do? Oh, that's a math problem. I must have to solve this. And then they'd solve it. Well, of course, you're going to get the same number. Writing in scientific notation does not change the number. It's going to be exactly the same.
And obviously.
At least it's a way to prove that.
So don't write it. Yeah, it is a way to prove it. You're right. But don't write it in standard form if it has to be written in scientific notation. It's already in standard form. I don't need it. I don't need to repeat it. All right, Caitlin. So where am I going to put the decimal point here?
And then the 2 and the 6, so.
Got it. Times.
10 to the negative.
Okay, so we're going to count 1, 2, 3, 4, 5, and 6. That is correct. There was our original decimal. Because we had to move back to the left, we have to backtrack. That's going to be times 10 to the negative 6.
if you've done 0.28 times 10 to the negative. Oh, wait.
0.28.
Yeah.
What happened to the 6?
Oh, my bad, never mind.
Also,
Oh,
0.28 is not between 1 and 10.
Yeah.
Okay, so just to clarify, in case you didn't catch that, writing numbers in scientific notation is pretty easy. Place the decimal after that first non-zero digit. That makes sure the numbers between 1 and 10, like it's supposed to be, can be equal to 1, can't be equal to 10. Because then if it's 10, now it's 1.0. So it's got to be between 1 and 10. Then count the number of times you have to move the decimal back to its original spot. If you move the decimal back to the right, you're going to use a positive exponent because that's a really big number. Big numbers require positive exponents. If you end up moving the decimal to the left, you're going to put a negative exponent. Because if you move the decimal to the left, like in our last problem where Caitlin had to move it to the left, that was because it was a really small number. Move it to the right, that's because it's a really big number.
I know you think of it.
Are you saying that it can't be 10? No.
What can't be 10?
Like 1 to 10, it can't be 10.
Correct.
The highest can be
Correct.
9.
I can't write it like this.
That'd be 100
Technically,
power
it'll just be
2.
1
You're right. It should be 1 times 10
then.
to 30.
Because if that was that, it would be like 10,000.
Right.
Yep.
Let's-
When you write a number greater than or equal to 1 and less than 10 in scientific notation, use 0 as the exponent. We already saw a number like this. We looked at the number 7. Right? One of the numbers we looked at was 7 times 10 to the 0. Since 10 to the 0 is 1, timesing 7 by 1 doesn't change the number. So if you're ever asked to take a number like 6, you write 6 in scientific notation, and you're like, do I just put 6? Do I put 6 times? You do have to write times 10 to the 0. Otherwise, it's not scientific notation. And I know that times 10 to the 0 is the same as timesing it by 1, but we write it as 10 to the 0 so that we can write it in scientific form. Okay, so if we have to take a number like this, or even if it's like this, if I said take the number 4.6 and write it in scientific notation, since 4.6 is already between 1 and 10, if I asked you where I have to put the decimal point to make that number between 1 and 10, you'd say it already is between 1 and 10. So technically, I'm moving it 0 times.
That's like typing, it's like seeing a problem where it says like the number times 1 and typing in calculator 6 times 1.
Yeah, that's true. Now, if the number was 0.46, that is not between 0 and 1. So then I would write 4.6 again. But because I had to put the decimal here and go back to its original location, I would put times 10 to the negative first power, which tells me it's actually smaller than 4.6. It's 0.46.
Wait. How would we know in that case where the decimal point was like original?
It's in, well,
Oh, the first non-zero.
it's purple. Yeah, you gotta put the decimal here, so it's between, yeah, that first non-zero digit, put it after that first non-zero digit, so that makes it between 1 and 10. Okay, so we're gonna write these numbers in scientific notation. And Jace has volunteered. Nice job, Jace. Thanks for raising your hand and volunteering. Jace, what would this number be in scientific notation?
It would be 2, 5.
You got it. Nice job. There's where my decimal needs to go. There's where my decimal currently is. So I have to move it to the right 1, 2, 3, 4, 5, 6, 7 spots. You'll notice that, you know, if you're timesing by 10 to the power of 3, that's 1,000. 10 to the power of 6 is 1,000,000 because of 6 zeros. So because this is 25 million, the more you work with scientific notation, the easier it is to, the quicker you are with it. I know that 25 million being one more place than just 1 million is going to be 10 to the 7th power instead of 10 to the 6th power, like all the other millions are. Okay. Dylan, I'm going to let you try example B. Decimal goes after the first non-zero digit. 1, 2, 3, 4. He had to move it to the left to get back to its original location. So he put -4. Perfect. This is perfect. I agree with this. Okay. Next one, example C. Next.
Obviously,
Well, you're doing C now.
Okay.
so
So you're gonna do 3.3 multiplied by 10 to negative exponent of 9.
Okay.
The negative exponent.
Oh, yes, it is negative. So there's where Max is putting the decimal. I agree with that. Here's the original location. And we have to move it 1, 2, 3, 4, 5, 6, 7, 8, and 9 times. So to the negative. That's you. Okay. Elise, I'm going to have you do example D since you had your hand up for the last one. You got it. Here's where you have to put the decimal. Here's its original location. Move it 2 spots to the right, so +2.
I'll put -2.
No,
yeah.
because only numbers that are decimals will have negative exponents. Here's my original decimal. I had to move it to the right to get back to its home. So if I have to move it to the right to get back to its original location, it's positive. If I have to move it to the left to get back to its original location, it's negative.
Okay, if we did like put the negative one, it's not negative, would you count like a half?
All right, so an album receives a Diamond Award when it sells 10 million copies. An album has sold 8,780,000 copies. How many more copies does it need to sell to receive a Diamond Award? Write your answer in scientific notation. So let's first off find out how many more albums we'd have to sell. You check.
I know the answer, but it's $1,220,000.
Okay.
That's great.
So that's how many more albums that this album would have to sell to go diamond. You've heard of like an album going platinum or something like that, gold or platinum. So diamond means you sell 10 million copies. We need to sell 1,220,000 more. So Nuche, how do I write this number so that it's in scientific notation?
It's 1.32 times 10 to the power 6.
You got it. I got to put the decimal right there. 1, 2, 3, 4, 5, 6 times 10 to the 6th. This will be the last thing we do today, and then we'll finish up with the last couple examples on Monday. Kind of seems like we're in science class, doesn't it?
Yes.
Remind me again what this is called.
Math. Language arts.
Space.
Scientific notation.
That's space.
So usually, a lot of times in science, when you study things, the things you study are very, very, very small, like atoms, cells, molecules, or the things you study are very, very, very big, like the distance between planets or the planets themselves or the sun, right? So they use scientific notation. So these numbers represent how many miles the planets are from Earth. No, from the sun, sorry. Match each planet with this distance from the sun. Then write each distance in scientific notation. Is it easier to compare the numbers in scientific notation or standard form? Well, the numbers here are in standard form. My argument is if we write them in scientific notation first, you'll actually find that they're easier to compare when they're in scientific notation than it is when they're written out like
You
this.
just look at that zeros, right?
Or we could just knock
Easier
out
to
all
look
the
at.
zeros.
All the big,
Or,
big
yeah,
numbers
put
are
it
the
further
further
away.
Very true. So for the first one,
Knock out the first set of two sets.
Harrison Bolden, how do I write this first number in scientific notation?
1.8 times 10.
Got it? Okay, so just to clarify, any number that is in the billions, not the 10 billions, but the billions, is gonna be times 10 to the 9. So if we see that again, okay? This number is in the 10 millions. So I'm gonna do this one for you guys. This will be 6.7 times 10. Because it's in the 10 millions, I'm gonna put times 10 to the 7th. Because I know 1 million has 6 zeros and 10 million has 7 zeros. Next one, Caitlin.
8.9 times 10 to the power.
Got it. 1 less than 10 to the power of 9, right? Because this is 100 million, not a billion, but 100 million. Okay. AJ Finney, example D.
143 times 10 to the power.
Good. This one has just as many zeros as example B did. Riley, example E.
1.4 times 10 to the power of B.
That's correct. Has just as many zeros as example C did. Devin, example F.
2.8 times 10 to the power of 9.
Got it. Yep. Has the same number of zeros as example A did. So it should be 2 to the 9th power. Levi, example G.
2.8 times 10 to the power of 8.
Good. And last one, Harrison.
3.6 times 10 to the power of 7.
All right. Now that the numbers are in scientific notation, we can order them very easily from least to greatest just by looking at the exponents. Trying to think of the easiest way to match them. I could just draw a line, I suppose.
Write their names beside it.
That's, yeah, let's just do that. That's easier. Okay, so which number here is the smallest? It's gotta be one of the 10 to the 7 numbers, right? So which one of those is the smallest?
That's
H.
Mercury.
Okay, so this gotta be Mercury. So let's just write Mercury.
Or you could put the letter by the.
But they have different, some of
Put
them, like
ME,
ME for Mercury.
but because Mars is high on Mercury.
How about Merc? Or just, might as well just finish it
Yeah,
right
I
now.
was just saying, 'cause these are like
What's the next smallest one? Venus, well, which one of those Venus then?
B.
6.
Yeah, so right now I'm only looking at these three right now. Because they're all the ones that had 10 to the 7th. So I know Mercury is the bottom one. I know 6.7 is smaller than 9.3. So this is gonna be the next smallest one. So this is Venus. And
the
which
other
makes
one's
this
gotta
one?
be Earth. Saturn.
Okay. So now I'm looking at the 10 to the 8th powers. Which of those three is the, ooh, I can't really see that one. Well, actually, you can see it better on the screen than I can see it on mine. Which of those is the smallest?
E. Mars.
This one here, 1.4. So that one's gotta be Mars.
Wait, why do all the planets look bigger than Mars? That was supposed to be smaller.
Mars is very small, or Mars is very small, that's why.
Oh, it's how far.
Yeah, it's not their size, it's how far they are from the sun. Okay, so we got this one now. Which of the remaining two is the smallest? G, 4.8, so that's Jupiter.
That's weird, I use red too.
And then after Jupiter is Saturn. Now we're looking at the ones that are 10 times 10 to the 9th miles away. This one and this one.
Uranus.
What'd you just say?
Uranus.
Hey,
Okay.
don't say that bad word.
Actually,
I mean, you're right.
Anus is not a bad word at all. Just a body part like every other. It's like same finger.
Caleb always says.
Toe.
You said no.
What comes after
Neptune.
Uranus? Neptune?
It's Uranus. It's not
You
Uranus.
said nostril. That's such a bad word.
What comes after Neptune?
Pluto.
Pluto.
Hey,
Asteroid.
I'm still holding out that Pluto might one day come back and join this planet.
Yeah. Pluto.
Right. That's where we'll stop today, and we'll finish those up briefly on Monday. I'm gonna give you guys your packets. While I'm giving you the packets, go ahead and use the restroom and come back in here.
Yeah.